Hi, I'm Nick, and I'm here to talk about scalable spectrum. So this, again, is really tightly related to what Mark was just mentioning. So with IQ data in particular, we have this big problem that IQ data is extremely voluminous and unstructured, which makes it hard to share and hard to scale. So, but we often start at looking just at the spectrogram itself. And the question is, can we make at least the spectrogram itself scalable to extremely large bandwidths and very easy to share? So what exactly would scalability be for a spectrogram? Well, we would need to have some data structure that even as your bandwidth explodes and your duration of your collection explodes, and as the number of concurrent clients grows, you still have constant time latency for your queries. And then, we want to get something without having explosive compute in the process. So the data storage and the CPU needs to be efficient, which is basically a constant growth compared to your base spectrogram. And your RAM needs to be good enough, so at least like sublinear, for it to be reasonable. And so with a system like this was what I've developed. It enables this data structure generation framework where you have things either at the edge, in the cloud, or on your normal collection systems that makes these manageable sizes of data that can then be fed to data retrieval systems that work on, again, on like standard client devices like an Android phone, which I have now as my system, where you can pan, zoom, tag, and share the data easily that then can feed machine learning systems. So it's basically like a data curation system. And then the long-term intent is that the machine learning can then leverage that and then help the humans with these large scale systems. So that way they can kind of work in concert with one another. And so the example I have here is in the data is stored. It's about 1 terabyte in AWS being sent to a smartphone. This is specifically the Breakthrough Listen Voyager 1 data set. And this will load, so it's 187 megahertz wide, which you clearly can't send down in real time to a smartphone. But it loads in under 30 seconds, and then you have minimal latency after that point. You can just pan and zoom around and kind of show it off as like an educational tool to young kids. The kids get super excited about it. Like, oh my gosh, space probe. It's on a phone. And this allows you to pan zoom in time, frequency, and power. So within a few seconds, you can get to this point. Here, let me see if I can do this and launch at the same time. I'll just mute it so I can keep talking while this is running. Where? Yeah, so you can move through the data easily, and as you do so, it'll pull an appropriate resolution for your screen display, so you can see the data in like it's kind of like faster than real time, but it's at appropriate time for you to go through yourself. I'm running out of time here, so let me just jump through this real quick. So yeah, the next steps for this has been like a thing I've done on the side. I'm trying to take it out of the prototype stage. So I'm really excited to engage with other people, find people interested in like really large scale data set curation, really large scale machine learning, and kind of figure out what sorts of constraints people are operating in. Everyone's got all these different constraints. What sorts of clients and user interfaces. I mean, I've done Android development, that's why it's there, but it can be applicable for a web thing or a Windows thing or whatever. Yeah, so feel free to contact me at any point. It's nick.richard@radwave.com. I'm really excited to get some forward progress on this. Thanks.